Lesson 8.5, page 157, problem number 22. You have this car going around a corner. So you see, oh look, the car's going in a circular path. If it's going in a circular path, you know there has to be an overall force acting towards the center of the circle. So the question is, exactly, what's providing the centripetal force? And in this case, it's not a tension force. There's no strain pointing inward. There's not a massive planet with a gravitational force pointing inward. What's providing that centripetal force? Friction. It's a bizarre sideways friction force. It's not the typical friction acting in the opposite direction of the velocity, because we know the velocity is this way. So normally the friction force is in the opposite direction there. It's not that friction force. No, no, no. It's a sideways friction force, which is acting towards the center. So we go and we apply the circular motion formula, m equals v squared over r. Fc equals mv squared over r. And for the centripetal force, we put in the force of friction. Now, even though the tires are turning, if they're turning and they're not sliding sideways, the two surfaces in contact, even though that tire comes around and then goes around, even though it's a turning tire, if the two surfaces, the tire and the road, aren't sliding relative to each other, what kind of a friction force is it? Static. So it's a static friction force. Now, if the car is going at a maximum velocity where the tires are just holding on, then you're going to max out that static friction force. And what is the maximum static friction force end up equaling to? Well, that is true. That is true. We already have that here. But basically, we know that if this velocity here is the maximum, and it's going really fast, then this static friction force is going to be at a maximum. And there's a formula, a friction formula for finding the maximum static friction force. Right. So this becomes ba-bam, mu sub s, the texture number, times the normal force. That's what the left-hand side becomes. That's what we're going to substitute in for the friction force. Mu sub s times the normal force. And the right-hand side remains the mass of the car, v squared over r. Now, usually, what is the normal force simply equal to? mg, the weight of the car. But this particular car, it's a little bit more complicated. We need to take a look at a side view. This car is like a race car. And the car's going this way, say. On the back of the car, you might have seen, it's got this like, it's got this little fin. Did you ever see like on the back of even like regular cars, like on the trunk, they have like a little fin, like a little tail fin, yes? Well, this little fin, when the air goes around it, the air actually is forced going underneath it faster than the air above, and it's this thing called the Bernoulli effect. And this little fin, due to the way the air is going above and below it, ends up force, and usually the normal force is just plainly equal to the weight force. But in this problem, guess what it's equal to? Exactly. And they tell you that force of the fin is 11,000 newtons. And then the weight of the car, well, they tell you that it's an 830 kilogram car. So then this FG here is going to be 830 kilograms times 10 meters per second squared. So all of that is the normal force, which is going to go in here, and then you could solve for the velocity. They gave you mu, they gave you the mass of the car, they gave you r, so then you solve for the velocity.
Wait, I thought the. Wait, don't you solve for mu?
Oh, you're right. They tell you how fast